Hybridization of atomic orbitals. First point about it is that it is a hypothetical concept. Second, only those orbitals of an atom whose energies are comparable take part in this concept. Third, it is a concept of mixing of orbitals. Hence it is immaterial whether orbitals are empty or possess single electron or even a pair. Fourth, the number of hybrid orbitals produced will be equal to the total number of orbitals taking part in hybridization. Fifth, the hybrid orbitals produced as a result of some type of hybridization will be of same energy, that is, degenerate. Sixth, the electrons possessed by parent orbitals will be filled in the newly formed hybrid orbitals according to Hund's rule. Seventh, all hybrid orbitals have directional character. That is, these will be directed in the space about the atom depending on the type of hybridization. Since hybrid orbitals can overlap due to a specific direction to a larger extent than the pure orbitals, hence bonds formed by hybrid orbitals are stronger and directional. Following table gives the geometries of different types of hybridizations. Thus we see in this table that due to sp hybridization, the two sp hybrid orbitals are formed at an angle of 180 degrees. So they are linearly arranged about the atom. As a result of sp2 hybridization, three sp2 hybrid orbitals are formed and they are directed towards the three corners of an equilateral triangle. So the geometry is plane triangular. Angle between the two hybrid orbitals is obviously 120 degrees. For sp3 hybridization, four sp3 hybrid orbitals are formed, which are directed towards the four corners of a regular tetrahedron. The angle between the two hybrid orbitals is the tetrahedral angle of 109.5 degrees. In case of sp3d hybridization, 5 sp3d hybrid orbitals are formed, which are directed towards the five corners of a trigonal bipyramid, such that three are towards the three corners of an equilateral triangle and two are above and below the plane of the triangle, so that equatorial angle is 120 degree and angle between axial and equatorial direction is 90 degree. In case of sp3d2 hybridization, 6 sp3d2 hybrid orbitals will be formed, which will be directed towards the six corners of an octahedron, which being a symmetrical figure, angle between two hybrid orbitals will be 90 degree. Again, there is a very, very important note. The first point of that is, besides sp3d2, sp3d3 hybridization is also possible. The 7 hybrid orbitals thus produced are directed towards the 7 corners of a pentagonal bipyramid from its center. Second point is, in case of hybridization involving d orbitals, that is sp3d, sp3d2 and sp3d3, can also be presented as dsp3, d2sp3 and d3sp3 respectively, for simple covalent compounds, of course. But in case of metal complexes, also known as coordination compounds, these will have a difference that in former outer d orbital or orbitals, and in the latter case inner d orbital or orbitals will be used. Third point is, though in most of the cases pi bonds are formed by pure p or d orbitals, s orbitals do not form pi bonds. But in some rare cases, hybrid orbitals can also form pi bonds. Fourth point is, if we can draw Lewis dot structure for a given molecule or polyatomic ion, then the type of hybridization the central atom will show can be decided by steric number rule, which was given by Gillespie. According to this rule, steric number of an atom is equal to number of atoms immediately bonded with that atom plus number of lone pairs of electrons on that atom. Mind it, this rule does not work for odd electron molecules and free radicals.